All right, for the Chapter 3 review, reminder, this is not the only thing you should be using to prep for the test. That curve sketching packet that I gave back to you that I graded, that's a big thing. Those have AP problems. And remember, our test is made up of 10 multiple choice and 2 free response. So also there's an optional AP classroom that you should definitely run through at some point. Okay. Find the intervals where the function is concave up or concave down. So you've got to have this in your head that concavity is based on the second derivative. So I'm going to find the first derivative. So the first derivative would be 24x squared plus 4x to the third. And the second derivative would be 48x plus 12x squared. And we want to find possible inflection points. So we're going to set f double prime equal to 0. So these are the pips. I can factor out a 12x, and that leaves me with 4 plus x. And so possible inflection points are 0 and negative 4. I need to put those on a number line. So negative 4 would be on the left, 0 would be on the right. We are testing into f double prime, and that's going to tell us about concavity for f. So now f double prime, you don't really need to test numbers. You can say, oh, f double prime is quadratic. It looks like this, which means f double prime is positive on the left, negative in the middle, positive on the right. And that means that f is concave up, concave down, concave up. All right. So I'm not practicing my justifying here. That's what you would have done in the AP packet. I'm just practicing the skills here. So concave up, that's negative infinity to negative 4 and 0 to infinity. And concave down is negative 4 to 0. For number 2, find the relative extrema using the first derivative test. So first derivative test is find the first derivative. So 2 times 2/3 will be 4/3. And then this will be x to the negative 1/3 minus 4. And because I want to find where f prime is equal to 0 or undefined, I need to get this into a single denominator. So right now it's 4 over 3x to the 1/3 minus 4. So I need to multiply 4 by 3x to the third over 3x to the third. So this is going to be 4 minus 4 times 3x to the 1/3, top and bottom, is minus 12x to the 1/3. And then it would all be over 3x to the 1/3. So this is f prime. And for the critical numbers could happen when the numerator is equal to 0. So when 4 equals 12x to the 1/3, 1/3 equals x to the 1/3. Be careful with this. I remember, I'm sure this happens on the test at some point. Sometimes people cube root both sides, but remember, you're raising both sides to the third in this case. So that would be 1/27th. So x equals 1/27th. Or from here, we get 3x to the 1/3 equals 0, so x equals 0. So those are critical numbers. They need to go on a number line. So 0 would be on the left, and 1/27th would be on the right. All right, we can't just sketch this graph because this is some sort of weird rational graph. So we do need to plug numbers in. So if I plug in negative 1, for example, I'm going to get 4 minus 12. Negative 1 to the 1/3 is negative 1. And then it's over 3 times negative 1 to the 1/3, which is still negative 1. So this is 4 plus 12 over negative 3. So that's a negative overall. And then this is kind of annoying. We've got to pick something between 0 and 1/27th. I would pick another fraction that's a perfect cube. Like I would pick 1/64th. That's smaller than 1/27th, and I'll be able to cube root it. So that would give me 4 minus 12 times the cube root of 1/64th is 1/4 over 3 times cube root of 1/64th, 1/4. So that's 4 minus 3 over 3/4. A positive over a positive. So this is positive. And then something to the right of 1/27th would be like, what if you plug in 1? You get 4 minus 12 over 3. That's back to being negative. So f decreases, increases, decreases. And remember, on your test, you don't get credit for any of this work that you just did. You need to come up with the right answers. And if you had to justify, you would have to say this in words. There is a relative min at 0. And what do I get when I plug in 0? Back into the original, I get 0. So there's a relative min at 0, 0. That would be because f prime changes from negative to positive. And what is the excuse me, what is the relative max? Well, the x coordinate is 1/27. So what is f of that? That's going to take a bit of math, right? So it's 2 times the cube root of 1/27 is 1/3, and then raise that to the second power, and then it'd be minus 4 times 1/27. So, this is ugly. Okay, so this becomes 2/9 minus 4/27. 2/9 multiplied by 3 becomes 6/27 minus 4/27, so 2/27. Interesting. So that's our relative max. And again, if I had to justify it, I would say because f prime changes from positive to negative. All right. State the absolute extrema of the function over the indicated interval. So this, excuse me, in our notes, this was the extreme value theorem. So remember, absolute extrema can occur either at the endpoints or the relative extrema. So let's find our critical numbers. So begin by finding g prime. G prime is equal to 4 times 5 minus 2x to the third. And then the derivative of 5 minus 2x is negative 2. Remember to chain rule. So g prime, actually, I'm just going to, so 0, when I set this equal to 0, it's equal to negative 8 times 5 minus 2x to the third. All right, so the negative 8 does not give me a critical number. If 5 minus 2x is equal to 0, then x equals 5 over 2. So the candidates for absolute extrema are x equals 1, or I should probably put an x here, sorry. X and g of x. Okay, there we go. This looks better. The endpoints, 1 and 5, or the critical number, 5 over 2. And I don't even know if this is a relative max or min or whatever. I'm just putting it in. Okay, so then we plug these numbers in and we see what we get. So what is g of 1? G of 1 is 5 minus 2 to the fourth. 3 to the fourth is 81. Plug in 5. You get 5 minus 10 to the fourth. Negative 5 to the fourth. What is that? 625, I think. All right, and then put in 5 over 2. When you put in 5 over 2, you get 5 minus 2 times 5 over 2. 5 minus 5 to the fourth. That's 0. Okay, so I can see what's the min and what's the max. This is the absolute max. This is the absolute min. So there's a max value of 625 at the ordered pair 5, 625. There's a minimum value of 0 at the ordered pair 5 halves 0. Find all points of inflection. That means you need x and y coordinates for your final answer. For this graph, and we're on, this is 2 full unit circles. So let's begin by finding points of inflection are f double prime, right? So let's begin by finding f prime. So that's 1/2. And then the derivative of cosine of x over 2. Remember, you have a cosine function and you have an x over 2. So the derivative of cosine, excuse me, is negative sine. So this is going to become plus because there's already a minus here. So plus sine of x over 2. And you're going to have to multiply by the derivative of x over 2, which is 1/2. So that's chain rule. This is f prime. Let's clean it up a bit. 1/2 plus 1/2 sine of x over 2. Okay, that's f prime. I'm talking about points of inflection, so I want to find f double prime. So f double prime, the second derivative, this 1/2 goes away. And so now I have, let's see, 1/2 sine. So what's the derivative of sine? It's cosine. So 1/2 cosine of x over 2. And what's the derivative of x over 2? 1/2. So f double prime of x is 1/4 cosine of x over 2. Okay, we need to find, we're looking for points of inflection. So the possible points of inflection, possible inflection points, the pips, are when cosine of x over 2 is equal to 0. All right, so on 2 unit circles, let's start on 1 unit circle. Where is cosine equal to 0? So remember, cosine, we're talking about the x values. So the x values are 0 at the top and the bottom of the unit circle. So that's when x over 2 equals pi over 2, and when x over 2 equals 3 pi over 2. Now, if I solve those for x, I need to multiply by 2. So x equals pi, and x equals 3 pi. That's why this was bumped out from 0 to 4 pi. So I'm not going to have to come up with more answers. If these answers were still within 1 unit circle, I would have to keep generating more. Like if this were cosine of 2x here, I would have to keep going and get 4 answers instead of just 2. But yeah, we get these 2 pips. And then remember, you need to put them on a number line to know if they're actually points of inflection. So pi, 3 pi. We're going between 0 and 4 pi. We're looking at the f double prime graph. Now, this is a cosine graph without a shift. So you could sketch a little cosine graph if you remember what that looks like. Or you can plug in points. Remember, even though we're not including 0 and 4 pi, we can still plug them in to see what the behavior is of the cosine function. So if I plug in 0, I get 1/4 cosine of 0, which is 1/4 times 1, so positive. What's between pi and 3 pi? Anything I want, right? So what's between pi and 3 pi? I'm going to put in 3 pi over 2. Or no, that's silly. I'm going to put in 2 pi. What if I put in 2 pi? It's 1/4 cosine of, it's x over 2, so 2 pi over 2. When I started saying I'm going to put in 3 pi over 2, that would have been silly because I would have had a 3 pi over 4 here, and that is not as nice. This is really just 1/4 cosine of pi. So 1/4 times -1 is negative. And then if I plug in 4 pi, which is the same as 2 pi, which is the same as 0 in the position anyway, coterminal, I should also get 1/4 times cosine of 4 pi. I should also get 1/4 times 1, so that's positive. So because f double prime changed signs at both pi and 3 pi, I have a point of inflection. So there are points of inflection at pi and 3 pi. I haven't found the y coordinates yet. I do that by plugging back in. So let's see. So what is f of pi? That would be 1/2 pi, so pi over 2, minus the cosine of pi over 2, because I'm plugging into x over 2. So cosine of pi over 2 is 0. So f of pi is equal to pi over 2. And what about 3 pi? F of 3 pi, so half of 3 pi, or 3 pi over 2, minus the cosine of, again, x over 2, so 3 pi over 2. Well, that's also 0, so 3 pi over 2. Okay, for number 5, find the relative extrema using the second derivative test if applicable. So remember, second derivative test is only applicable if f double prime of c, your critical number, is not equal to 0. So let's see if it works or not. Find f prime. Here are the steps for second derivative test. Again, some of this test, you're going to need to do a bit of studying of what is the first derivative test, what do I do for that, what do I do for second derivative test, what do I do for concavity, points of inflection, like go through and run through those steps again. Anyway, f prime, here's how we start this. So this is going to become just 3 times 1/3 and then x squared plus 2x minus 3. So first you find f prime. Second, you find critical numbers. So when is this thing equal to 0? Let's factor it. Okay, so critical numbers are -3 and 1. Step 3 is not to do the first derivative test, which is put those on a number line and see what f prime is doing. Instead, you find f double prime, find that equation, excuse me, that's 2x plus 2. Now plug in these values. So step 4 is evaluate f double prime at each value. So when I plug in -3, I get -6 plus 2. I get -4. So f double prime of -3 is less than 0. And when I plug in 1, I get 2 plus 2 is +4. So f double prime of 1 is greater than 0. What does f double prime being less than 0 mean? It means at -3, the graph of f is concave down. And at 1, the graph of f is concave up. So there's a relative max at -3 and a relative min at +1. All right, and then what are those values? So what is f of -3? So I've got to plug back into here. So it's 1/3 times -27 plus 9 plus 9 plus 1. Well, third of -27 is -9 plus 9 plus 9 plus 1. So 9 plus 1 is 10. So there's a relative max at -3, +10. And then the relative min is at 1. So plug in 1, you get 1/3 plus 1 minus 3 plus 1. Okay, so 1/3 and then 2 minus 3. So 1/3 minus 1. That's -2/3. All right, so when I plug in 1, I get -2/3. What would my justification be? If I had to justify this, it would be here, it would be because f prime of 1 equals 0 and f double prime of 1 greater than 0. And here it would be, this is a max because f prime of -3 equals 0 and f double prime of -3 is less than 0. Those would be my justifications if we had to do that. Okay, what about number 6? Find the intervals on which the function is increasing. So when do I want to know if something is increasing? I take its derivative and find where the derivative is positive. So where is f prime greater than 0? All right, so in order to do that, let's find f prime. F prime is going to require a little bit of a product rule because I don't feel like expanding this out to the 5th power. So although I could, well, anyway, whatever. Throw back to Pascal's triangle. I could kind of quickly do that, but that would take some remembering. So anyway, we won't worry about that. Why bother when we could just do product rule? So first times derivative of the second. Chain rule, technically, derivative of x plus 4 is 1. I like putting that in there because if it's if you just get in the habit of seeing an expression and chain ruling it just to be sure, then you won't miss things like when is it negative or whatever. Okay. First times derivative of the second plus second times derivative of the first. So let's clean that up. So this is 5x times x plus 4 to the 4th. And then really just plus x plus 4 to the 5th. And remember, we're trying to find the zeros for this thing. So let's start factoring it out. Set it equal to 0 because we're trying to find critical numbers. I can factor out an x plus 4 to the 4th, which would leave me with 5x plus x plus 4 to the 1st. And the only reason I include parentheses there is because if this is minus in between, then I've got to distribute the negative through. So good habit to get into. You're supposed to clean up these parentheses. 5x plus x is 6x plus 4. Okay, so what are the critical numbers? X equals -4 and subtract 4, divide by 6. So -2/3, right? If you subtract 4 and divide by 6. Put those on a number line. -4 would be to the left of -2/3. You're testing into f prime, and you're looking for where is f increasing. So where is f prime positive? Now, remember, f prime, look at this. If you were to FOIL this out, it would be 6x to the 5th plus some other stuff. So I know that the end behavior, if you want to do this by graphing, I know that the end behavior is up on the right, down on the left. The graph should be bouncing, touching and turning at -4, and crossing through or changing signs at -2/3. If you don't remember all the graphing rules, then just test numbers, plug in -5, plug in -1, and plug in 0 and just see what you get. But you should get minus, minus, plus. So the only place that this function is, that f of x is positive is, or I'm sorry, the only place that f prime is positive is over here. And that's the only place where f is increasing. And I use open parentheses because we don't consider the turning points where you have a relative max or min. I don't consider that to be increasing. So -2/3 to infinity, and my reason, if I needed one, would be because f prime of x is greater than 0. If you're going to include -2/3, which again, I wouldn't, but if you did include that, this would have to say greater than or equal to 0. But let's just not do that. Okay, number 7, find all relative extrema and increasing, decreasing intervals. Okay, so we can either do quotient rule or product rule. Let's do quotient rule with this one. If you're not a fan of factoring out parentheses like we just did, then you should probably stick with quotient rule for a lot of these. So what is f prime going to be? It's low, d high, so derivative of x squared is 2x, minus high, d low, derivative of x squared minus 4 is also 2x, all over low, low. And then we can distribute what we have up here. So we have 2x to the third minus 8x minus 2x to the third. The 2x to the thirds cancel. So f prime of x is equal to -8x over x squared minus 4 squared. Now, I don't want to sketch this graph, but I do have to put critical numbers on a number line. So what are the critical numbers? X equals 0 is when f prime is equal to 0, and plus or minus 2 would be where f prime is undefined. -2, 0, 2. We're testing into f prime and talking about f. So let's start with -3. If I plug that in here, I get I get positive 24 over, now don't do more math than you need to. This denominator is something squared. So it doesn't matter what the thing is that's squared. That's positive no matter what. So a positive over an always positive is positive. Plug in -1, you get 8 over an always positive, positive. Plug in, one thing I forgot to do, x is not continuous at plus or minus 2, so we should be putting vertical asymptotes here so that we don't accidentally say that these are going to be relative max or min points, or that we're increasing on the interval where there's an asymptote. Okay, anyway, plug in 1 and you get -8 over an always positive. So that's negative. And same thing with plugging in 3, you're going to get -24 over an always positive. So that's negative as well. So where is there a relative min or max? Okay, so f is increasing, increasing, decreasing, decreasing. So the only changeover from increasing to decreasing is at 0. So there's no relative min. There is a relative max. When x is 0, f is 0 over -4, so f is 0. Where is the graph increasing? So you can't say -infinity to 0. You have to leave -2 out, because this graph is one of those ones with like branches like this. It's something like this. I'm just making it up. But yeah, so I can't say that it's increasing at -2 because it's not. Okay, so increasing from -infinity to -2 and -2 to 0. Basically, when you're doing increasing, decreasing, or any of these, you should be doing a quick little domain exclusion anytime you have a number line. It hasn't popped up yet because we haven't had any other discontinuities. But when f is rational, write down the asymptotes. Okay, so positive on those, or increasing on those intervals, excuse me, and decreasing on 0 to 2 and 2 to infinity. Okay, find the concave up and concave down intervals and the points of inflection for this graph. So concavity is based on second derivative, so let's get there. So f prime is equal to 4x cubed plus 2x. F double prime is equal to 12x squared plus 2. Set this equal to 0. Now you should be running into a problem here. You can like factor out a 2, I guess, if you want to. When is 6x squared plus 1 equal to 0? Never. 6x squared is never equal to negative 1. X squared is never equal to negative 1/6. Or if you don't recognize this all along the way, if you get an imaginary for x, it means there are no real numbers that make this equal to 0. We still need to think about what is f double prime doing. So there is no place where f double prime equals 0 or undefined, but 6x squared plus 1 or 12x squared plus 2 is always greater than 0. So this graph is always concave up. There are no discontinuities, so it's concave up from negative infinity to infinity. It's never concave down, and because the graph never switches concavity, there's no point of inflection. Find the relative extrema, excuse me, for this function. I'm going to rewrite it with an exponent just so I have that to look at. Okay, relative extrema, that's first derivative. So f prime of x, I need product rule here. It's equal to first times derivative of the second. That's 1/2, 4 minus x to the negative 1/2 times, what's the derivative of 4 minus x? Negative 1. That's an important detail. We'll see that a lot in our AP problems. Plus second times derivative of the first. We need this to be equal to 0, so let's clean it up a bit. So this is negative 1/2 x times 4 minus x to the negative 1/2 plus 4 minus x to the 1/2. Let's factor a bit. We did this in our notes, I think. Let's factor out a negative 1/2. And what do you get when you do that? Remember, you are dividing. When you say you're going to factor something out, let me leave some room here. If I say I'm going to factor out a negative 1/2, I'm going to divide by negative 1/2 each term. I also want to factor out the 4 minus x to the negative 1/2 because that's the smaller of the two exponents. So if I am factoring that out, all of that, the question is, what are you left with in the square brackets? So the negative 1/2s cancel, the parentheses cancel, you're just left with an x from the first term. And then if I have 1 divided by negative 1/2, I really have minus 2. And then what am I left with here? 1/2 minus negative 1/2 is 4 minus x to the first. Okay, and what else should I do with this? Well, I should get rid of the negative exponent and clean this up here. So when is 0 equal to, so what do we get up here? We get, there's a negative 1/2, there's negative 1 out front. In the square brackets, I distribute this. I get x plus 2x is 3x. Negative 2 times 4 is minus 8. What's in the denominator? The 2 from the 1/2, negative 1/2. And the 4 minus x, it's now to the 1/2 down here. Okay, and then we need to test into, we need to find our critical numbers. So x equals add 8 divided by 3, or x could also equal 4. It seems like, again, this is going to be kind of rough to test into, but remember, well, I'll talk about it in a minute. So, okay, 8/3, that's what? That's 2 and 2/3, so that's on the left. And then 4 is over here. We're plugging into f prime. Now, look at what you have down here. Remember, something to the 1/2 is really square root. And the reason I point that out is because, remember, square roots are always positive. If we're plugging in values in a domain, those numbers are always positive. What numbers are in the domain, by the way? Let's do a quick little domain check. 4 minus x needs to remain greater than or equal to 0. 4 needs to remain greater than or equal to x. So really, x needs to stay less than or equal to 4 if I flip that around. So I don't even have to bother with this interval, greater than 4. I only need these two. All right, 0 is over here. So if I plug in 0, I get negative 0 minus 8 over 2 times square root of 4. So this is positive 8 over a positive. So that's positive. And then something between 2 and 2/3 and 4. So if I plug in 3, I get negative 9 minus 8 over 2 times square root of 4 minus 3. So this is negative 1 on top over a positive, so that's negative. So f increases, then decreases. That means that there is no relative min because I can't plug in anything. If I plug in 5, I'm going to get an imaginary. So there's no changeover. And then there is a relative max. It's when x is 8/3. And what is f of 8/3? My goodness. Okay, 8/3 times the square root of, instead of 4 minus 8/3, let's make that 12/3 minus 8/3. That's 8/3 times the square root of 4/3. So, gosh, 8 times 2 would be 16 over 3 radical 3. Let's not rationalize. We don't need to for our AP test. Okay, and let's see. Find the intervals where G is concave up or concave down. Okay, so here's G. We're on 1 unit circle. G prime of x is equal to cosine x minus sine x. And what's G double prime? Because we're looking at concavity. Negative sine x minus cosine x. Okay, let's find our values here. 0 equals negative sine x minus cosine x. Let's think about this one a bit. Add sine x over here. When is sine x equal to negative cosine x? When are they equal to each other? They're equal to each other at pi over 4, right? They're both radical 2 over 2. And at at 3 pi, what is this? In quadrant 3, what is this one? 5 pi over 4. Thank you. There we go. They're both negative. They're both the same here. That means they're opposites. Sine is positive radical 2 over 2, and cosine is negative radical 2 over 2 in quadrants 2, and then flip that in quadrant 4. Oh, wait. What am I doing? Sorry. Cosine's the x, sine's the y. Wow. And then cosine's positive radical 2 over 2, and sine is negative. I knew something was wrong because my points were plotted backwards. Okay, so they're opposites at these two angles. So what are the critical numbers here? The critical numbers are 3 pi over 4 and 7 pi over 4. And we can test into this if we want to. 3 pi over 4, 7 pi over 4, between 0 and 2 pi. Okay, so I'm going to plug in 0 into negative sine minus cosine. So negative sine of 0 minus cosine of 0. Sine of 0 is 0. Cosine of 0 is 1, so this is minus 1. What's between 3 pi over 4 and 7 pi over 4? Use a non-quadrant angle. I'm going to choose pi. So plug pi in. Negative sine of pi minus cosine of pi. Sine of pi is 0. Minus negative 1 is 1. And then something between 7 pi over 4 and 2 pi. Remember, you can pick the end, 2 pi. And that should be the same thing that happened at 0 happens at 2 pi. So that's negative. So that's what's happening with G double prime. That means that G is concave down, concave up, concave down. So concave up between 3 pi over 4 and 7 pi over 4. And concave down from, remember, our endpoints are set for us, so it's not negative infinity. It's 0, we are including 0. Oh, my pen stopped working. Uh-oh. There we go. 0 to 3 pi over 4 and 7 pi over 4 to 2 pi. I am including these endpoints because when I plugged in 0, I got a negative. So the graph of G is concave down because its second derivative is negative at those 2 points. Number 11. I'm probably going to get cut off here before our class starts, so we'll see how far we get for this. Find the intervals where the function is concave up or concave down. Find points of inflection. We might need a calculator. Okay? Well, if I'm allowed to use a calculator, then I'm allowed to use the calculator for the whole thing. So here's what I would do. Find f prime. That's 4x, let's see, and then plus 2 cosine of 2x times the derivative of 2x. So f prime is 4x plus 4 cosine of 2x. Now, if I'm allowed to use a calculator, then a point of inflection would be where f prime has relative extrema. And concavity would be where f prime is increasing or decreasing. Or if you want to go through and find f double prime, then you could find f double prime. It's 4 minus 4 sine of 2x times 2. So it's 4 minus 8 sine 2x. So you could say, okay, well, I'm going to have a point of inflection where f double prime changes signs. So it depends on if you do this or this. I'm going to go with f double prime since I took the trouble to find it. So I'm hopping over to my calculator and I'm typing in 4 minus, what was this? Let me split screen here. 4 minus 8 sine of 2x. I'm making sure my calculator is in radian mode for all of you physics degree people there. And how do I get this to show up? We're looking on the interval. It says look on the interval 0 to pi. So remember from last year, set your window 0 to pi, and then zoom fit, which is option 0. Once you set your domain, you zoom fit, and it will fit this to the window. See how the window is still 0 to pi? So this is the portion of the graph I want. All right, and this is f double prime. So the graph is concave up where f double prime is above 0. So let's figure out what these two coordinates are. I like putting in y equals 0 and then just finding the intersection. I find that faster than using the 0 feature here. So that is totally up to you what you decide to do. All right, so let me find the one on the left first. 0.262. So 0.262, I'm just writing these down. And what is the other intersection point between my second derivative graph and 0? 1.308. 1.309. We always round to 3 places for our AP test. Okay. All right, so where is the graph concave up? So let's take a look. Let's take a look at the graph again. Let me split screen. So concave up is where the second derivative is equal to, or is positive. So, and we are including endpoints. So concave up from 0 to 0.262, and also from 1.309 all the way out to pi. And again, the endpoints are included. So the second derivative is positive at pi. Concave down in between 0.262 to 1.309. And then what about the points of inflection? Both of those are points of inflection because we're plugging them into f of x. So this is kind of annoying. I need to type in the full decimal for that value. Now here's something you can do. This is kind of clever. Well, no, shoot. I need to find the points of intersection. So, okay, so here was one of them. I'm going to write down the whole thing. 1.3089969. And let me find the other one real quick before my bell rings. 0.2. So this is really 0.2617994. So I don't want to use a rounded value in my answer to find these points of inflection, even though they might round okay to 3 places. I'm going to plug these decimals into f of x. All right, so let me split again here. All right, so Now, I like to do it like this. Again, we did this in pre-calc last year. I like to type the function into the calculator like this. And then on my calculator screen, I'm going to use function notation. I want it to find y of the first decimal. So 0.26179994. And then I'll round that to 3 places, so 1.137. So 1 point of inflection is at 0.262, 1.137. And then the other one is at 1.309. And what do I get when I type in that full decimal for that one? So that was 1.3089969. I get 4.427. So it is important not to use a rounded answer to then find another answer. That's going to throw things off. All right, we're stopping there for this video.